Okay, I guess you already know why I'm called TD and not by my full name. Okay, so I'm here to present discretized streams, and this is joint work with Mate HY, who also goes by his initials, Timothy Hunter, Scott, and Jan. And the motivation behind our work is that there are lots of big data applications that process large streams of data, and one needs to provide results in a near real-time manner. And from, you can take a number of examples. For example, a website monitoring system may would like to monitor a bunch of websites for load spikes, etc., and react to them as soon as possible. A fraud detection system may want to monitor bank transactions to check for frauds. An ad monetizing system may want to count the number of ad clicks that you have get in real-time fashion. Now, these are just a few examples. There are a lot of such applications, and the common property across all these applications is that they are large-scale. They require tens of hundreds of nodes to handle the streaming workloads, and they require end-to-end latencies of a few seconds. Now, the problem with large-scale systems is that you have to deal with faults, and not just with faults, but also with stragglers. And especially streaming systems need to recover from faults and stragglers quickly and efficiently. What do I mean by quickly and efficiently? I'll explain in a few minutes. But what I want to emphasize is that for a streaming system, it's even more necessary to recover from faults fast compared to a batch system, because let's say you have a fraud detection system, you don't want your fraud detection system to be down for a long time. Now, the traditional stream processing systems don't quite get these two properties right simultaneously. And I'm going to explain that in a bit, why. And so in this talk, this is the outline. I'm going to first talk about the limitations of traditional stream processing systems, then what we propose, discretized stream processing, and finally, how discretized stream processing unifies batch and stream processing models. Okay. So the way traditional stream processing systems work is that they use this continuous operator model, where in the processing pipeline, each node runs a continuous operator which maintains an in-memory mutable state. And as records come into the node, the in-memory mutable state is updated, and new records are generated and sent out to the downstream nodes. The problem with this model is that as soon as the node fails, the mutable state may be lost. And there has been various techniques developed to make this mutable state fault tolerant. I'm going to classify them in two large classes and talk about what are the limitations of each class. Okay, the first class of techniques that have been used by systems like Borealis and Flux is node replication, where a completely separate set of nodes also process the same stream in parallel with the primary set of nodes. These nodes act as hot failover nodes. And there is a set of synchronization protocols that makes sure that these set of nodes work in sync, that they make sure that the sequence of records they process is exactly the same, to make sure that the state that they generate is exactly the same. Now, when there is a failure in one of the primary nodes, the system automatically switches over to the secondary set of nodes immediately, and the system can continue processing with very little or no disruption at all, because the secondary set of nodes were already in sync. So you can see that here the failover is really fast, but it comes at the cost of twice the hardware. And in large-scale systems, if you want to run, let's say, a streaming workload on 100 machines, you do not want to run 200 machines just to handle one node failure. So this is not very desirable. The other technique that people have used is upstream backup, like systems like TimeStream and to some extent Storm, where each of the nodes in the pipeline maintains a backup of the records that it has forwarded to the downstream nodes, until the downstream node checkpoints its own state and acknowledges back that it has finished processing the records. For supporting one node fault, once another standby node, a cold failover node, is maintained in the system, and if the a node in the primary node fails, its upstream node essentially replays the backed up records serially to this failover node to recreate the state that was lost. And after the state has been recreated, the system continues to process as usual. Now here, it is clear that this is cheap from the hardware point of view, as you need only one backup node. But the failure recovery is slower because you need to replay the data and recompute the state after the failure occurs. So you can see that these two different models, you can either get fast recovery with twice the hardware cost, or get slow recovery for cheap. And common problem across both these systems is that they don't handle slow nodes or stragglers very well. Let's say one of the nodes in the system happily decides to slow down for some reason or the other. This would effectively slow down all the other downstream nodes in the pipeline. And in case of node replication, since the replicas has to stay in sync as well, this will slow down the replicas as well. So neither of these approaches handle stragglers. So we made this our goal, of an ambitious goal to build a system that scales to hundreds of nodes and achieve end-to-end latencies of order of few seconds, tolerates failures and stragglers, as well as achieve failure and straggler recovery within seconds, and with minimal overhead, minimal extra hardware beyond the base processing requirements. So we accepted the challenge and tried to understand why this is hard. So this is hard because the stateful continuous operators tightly integrate computation with the mutable state. As a result, what happens is that it is much harder to define clear boundaries between the mutable state and the computation where both of them can be moved around independently. Instead, what we propose is completely dissociating the computation from the state. Basically, make the state immutable and divide the computation into smaller, deterministic, stateless tasks. And the way the stateful computation is done is that you take the previous version of the state, apply a stateless task on it to generate the new version of the state, then again apply another stateless task to keep generating new version of the state, so on and so forth. This defines the clear boundaries at which the state and the computation can be moved around. Now this may seem very abstract at this point, but the neat thing is that there are already systems that does essentially this, which is basically batch processing systems. Especially systems like MapReduce, they already divide the data into small partitions and the jobs into small deterministic stateless MapReduce tasks. Let's quickly walk through an example of a MapReduce job to understand this better. Typically, you start with an immutable input data set, which is typically, let's say, a file in HDFS or GFS. And this file is already divided into smaller partitions. For each of the partition, a set of map tasks are executed. These map tasks are completely stateless, and the output they produce is also immutable. And these map outputs are shuffled together, and reduced tasks aggregate them to find, which are also stateless, by the way, and finally aggregated into the final immutable output data set. Now, because these tasks are stateless, they can be moved around very easily. Let's say if there is a couple of nodes fail in the system, and therefore we lose a couple of map tasks and a couple of reduced tasks, and a few of the partitions in the output data set that were supposed to be generated were not generated. What the system will automatically do is basically rerun these map tasks in parallel on the other nodes in the system. They will generate the same immutable map outputs, which will be again aggregated by reduced task rerun on other nodes in parallel and generate the partition that was supposed to be generated. And this parallel recovery is what we use in our stream processing model, which we call discretized stream processing. And the idea is essentially very simple. We take a streaming computation and run it as a series of small deterministic batch jobs. And the intermediate state that's supposed to persist across batches is stored in the memory, in the cluster's memory as an immutable data sets. Now, we also need to do a bit of engineering effort to make sure that these batches can be made as small as possible to ensure that we get an end-to-end latencies of a few seconds. Let me elaborate this, how this exactly works. So let's say between the time interval 0 to 1, all the data received from multiple streams in the stream processing system is collected and stored in the memory of the cluster. This input data set is replicated for fault tolerance. We apply then batch operations like MapReduce on this input data set and create a final output data set. Now, if it's just the output data set, then this can be pushed out to some external file, HDFS, or out to an external database or something like that. Or if it is a state data set, it is going to be reused later. Now, note that this state data set is not replicated. Then when the next set of input data comes in, we apply MapReduce jobs again on the input data set as well as the state data set to generate the next version of the state data set. And this sequence of input data sets and state data sets essentially forms the input stream and the state stream. Let's look at it from a developer's point of view, what programming using this model looks like. So the programming abstraction that we provide is called the discretized stream, or D-stream for short. And it's essentially a sequence of immutable partition data sets. These streams can be either created from live data stream, as shown in the short example. The read stream function creates a data stream with a batch size of 1 second from some external source. It has page views in it. And this stream can also be created by transforming using bulk parallel transformations existing data streams, as shown by the transformations map and running reduce. So this program, what essentially does, it keeps a running count of page views over a period of time. And underneath, the data sets that gets created is basically this. And as you can see, the blue data sets are basically the state data sets that aggregate the counts across batches. Now, what the system maintains is this fine-grained lineage of operations that led to the creation of each data set. This lineage is maintained at the granularity of partitions, as shown by the arrows. And this lineage is what is used to recompute when things get lost. And we don't want the lineage to grow too much because we don't want to limit the amount of recomputation necessary in case of failures. So we also periodically checkpoint some of the state RDDs to ensure the lineage is cut off. And the checkpoint is done asynchronously by saving the state to some stable storage, let's say HDFS or some database, and the lineage of that RDD is cut off. Now, this lineage is used to recompute lost partitions. Let's say there was a failure and we lose some of the partitions out here across different time intervals, as well as all the partitions in a data set within the single time interval. What the system would do is that it would look at the lineage and realize that these 3 different partitions in 3 different time intervals do not depend on each other. So it can recompute the lost partitions in parallel. Similarly, once those have been recomputed, it will find that the 3 lost partitions in that data set can also be recomputed in parallel. So it will recompute them in parallel. Now, if you compare this with Upstream Backup, the difference is as follows. So remember that Upstream Backup replays the whole sequence of stream in exactly the same order to a single standby node to recreate the mutable state. Compare this to our setup where the data stream is already divided into data sets, which are further divided into partitions, and the lineage essentially exposes all the dependencies and as well as all the partitions that can be recomputed in parallel. So it essentially exposes the parallelism both within a batch as well as data sets across time. So this essentially ensures faster recovery than Upstream Backup without incurring twice the cost of node replication. Let's try to see how much faster can it be from Upstream Backup. To understand this, we did a theoretical analysis. We defined recovery time as the time taken to recompute the lost data and catch up with the processing of the live stream. And clearly this depends on the amount of available resources in the cluster for recomputation, which in turn depends on the system load before failure. And as you can see from the graph, that lower system load means more available resources for recomputation, therefore lower recomputation time. Note that parallel recovery with 5 nodes is significantly faster than upstream backup. Also, parallel recovery with 10 nodes is significantly faster than that with 5 nodes as well. And this is because with 10 nodes, we just have more parallel available resources to exploit while recomputation. And therefore, it gets this processing model gets a very nice property that larger your cluster is, lower your recovery time can be. We can also use the same underlying principle to do straggler recovery as well. In batch processing system, typically straggler mitigation techniques involve detecting a slow node, let's say a slow task, let's say tasks that are running 2 times slower than other tasks in the map stage or reduce stage, and then speculatively launching more copies of those slow tasks on other nodes in parallel. The same technique can be used in our stream processing system as well, and essentially it can mask the impact of slow nodes or stragglers on the progress of the system. Let's evaluate this. And to evaluate this, we built this system called Spark Streaming, and it is implemented using the Spark processing engine. For those who are not familiar with Spark, it is a very fast batch processing system that allows data sets to be stored in memory, and it can automatically recompute lost partitions out of the data set based on lineage. We had to modify Spark's processing engine significantly to reduce job launching overheads from seconds to milliseconds in order to achieve end-to-end latencies of the order of few seconds. How fast is Spark Streaming? So in total, it can process 6 million records per second on 100 nodes, all with an end-to-end latency of 1 second. We tested this using 100 4-core EC2 instances and 100 streams of text. The workload was grep, which is shown in the left-hand side graph. Grep is basically a count of the sentences having a particular keyword. We also tried a more stateful computation, which is word count across a sliding window of last 30 seconds. In both cases, you can see that the throughput of the system increases linearly with respect to the size of the cluster. Also note that if you allow, instead of 1 second, if you allow 2 seconds to process, then the throughput can be slightly higher than that. To compare it with other existing commercial stream processing systems, we compared it with Oracle CEP, Esper, and Streambase, and we found that the throughput in records per second per core is comparable to these other systems, which shows that even with this crazy different processing model than traditional stream processing, we can achieve similar throughput that other stream processing systems provide. Note that the Oracle CEP, Esper, and Streambase are not distributed systems, but single node streaming processing systems. So we can definitely achieve a lot more aggregate throughput than these systems can provide. Finally, we also tested how fast it can recover from faults, and we tested this by introducing a failed node in the system in the middle of the streaming computation. As you can see from this graph, which shows the processing time of each batch on the y-axis and the timeline on x-axis. The batch after the failure took significantly more time, and then it improved as time went by. If you focus on the 2 green lines, those are the processing times with 40 and 20 nodes with 10-second checkpoints. And you can see that the recovery time of the 40 node is much faster than that of the 20 nodes, thus verifying the conjecture we had made using the theoretical analysis. If you compare the blue lines with the green lines, the blue lines have a higher checkpoint interval, 30-second checkpoints instead of 10. they have higher recovery time because you need to do more computations to recover. And so this graph shows that how the system behaves with respect to the size of the cluster as well as the checkpoint interval. There are more results in the paper. I encourage you to look at them. I'm only presenting some of them out here. We also tested how fast it can recover from stragglers by actually slowing down a node instead of killing it. And the results here show that before introducing a straggler, the processing time of each batch was around half a second. After introducing the straggler, it went up to 2 to 3 seconds in these two workloads. But after turning on speculative execution, the processing time came back down to sub-second levels, which essentially masks the effect of the straggler in the system. Finally, last but not the least at all, is the unification that we can achieve by with batch processing, interactive processing. So the discretized stream model, since it is based on the underlying batch processing model, allows a single programming model and execution engine to run both streaming and batch processing and interactive jobs. So what this allows you to do is combine live data streams with historic data. For example, compare live page views with historic page views that you have seen earlier. Or you can interactively query live data streams. For example, in this case, you can get records over a time interval and do batch jobs on it, in this case count. And this enabled us to create very easily write complex applications. So Mobile Millennium Project is another project back in UC Berkeley, which tries to do real-time estimation of traffic transit times using live and past GPS observations. So what it essentially does, it runs Markov chain Monte Carlo simulations and combines live and past GPS observations to do it. And it was very easy to write this program because we had Markov chain Monte Carlo simulation programs for batch jobs in the same project, and we just had to port those batch jobs to run on the streaming platform without very little modification. And you can see that this system scales very linearly with respect to the cluster size. Finally, before I complete, I would like to highlight some recent related work. Naiad, which is the talk you are going to listen next, takes a completely different approach for combining graph, streaming, and batch processing together in the same system without sacrificing latency, but which is awesome. But in terms of fault recovery, what the system does is it uses synchronous checkpointing, which compared to our asynchronous checkpointing, and in case of failure, the whole cluster, all the nodes in the cluster has to roll back to the previous checkpoint, and therefore replay and recompute the data once again, which can be significantly costly in certain workloads. SEEP is another paper which tries to extend the continuous operator model to enable parallel recovery, but it still does not handle stragglers like we try to explicitly do. TimeStream is another system which I touched upon. It is similar to Upstream Backup, so it has the same limitations as I've already discussed, and Millwheel stores the state in Bigtable, but it uses transactions per state update, which can be expensive. Finally, the takeaway is that a large-scale streaming system must explicitly handle faults and stragglers, and discretized streams model streaming computation as a sequence of batch jobs, which uses simple existing techniques to exploit parallelism within streams, allows it to scale to 100 nodes with 1 second latency, and recovers from failures and stragglers really fast. The Spark streaming system is completely open source. It is actually bundled with the Spark project. In fact, we released it last spring, and it is used in production by about 10 organizations already, and more than 40-50 organizations actually trying it out. So please try it out and give us more feedback. Thank you. I'm happy to take questions.
Okay. Well, I got a nice question from the sky here. It seems the state retained at each vertex across batches of input must be reprocessed each batch. And as this grows, it may increase the batch latency. How much state is hello, hello, hello. Here we go. It seems the state retained at each vertex across batches of input must be reprocessed each batch. And as this grows, it may increase the batch latency. How much state is retained in your experiments, and will latency stay small with 100 gigabytes of state?
That is a very good question. So, in our experiments, we have tested with about 1 to 10 gigabytes of state data, but we haven't explored this a lot. But what we believe we can do is within the constraints of the framework of immutable data sets, we can do low-level optimizations across immutable data sets to make sure that the state maintained doesn't need to be processed over and over again. So that is something we plan to do as part of our future work, but it is something we haven't explored in detail yet.
Philip Levis, Stanford University. So it's often the case in stream processing systems we care a lot about the timeliness of results, or actually knowing that we have the full set of a batch for a time window. So things like Millwheel have their watermarks. So this system doesn't. Is there something different about the application space such that you think that it's not as important for the class of things that you're processing, or?
Regarding the watermark, for example, so since we are processing in batches, we essentially creating an implicit watermark between time intervals anyways. So this, now a lot of streaming systems may work with this. Actually, we have found by speaking to developers that this sort of batching is intuitive for them to understand, and the second scale latencies that we achieve, which is more than a lot of streaming systems provide, but it is fine for a lot of their workloads. So yes, we do sacrifice a little bit of latency from that point of view, but the amount of advantage in fault tolerance and straggler mitigation that we get is a real boon for practical developers' point of view. Thank you, that was a good question. Yes.
Hi, Matt Oury from Princeton University. Just to follow up on the last question. A lot of the performance that you get out of the system is by using timestamps that are based on when the data entered Spark streaming. What about handling external timestamps and counting latency from the point of view of data generation, not the point of view of entry into your system? I imagine that this explodes the state that you need to maintain.
That is a very good question. So yes, we divide this data into batches based on the wall clock time of the receiving node. The way we can do use application time for processing is that by applying windows, we provide window operators out of the box on this batch of data, and using the window you can filter out the application level window of time that you want to process it on. So the framework doesn't stop you from doing that, and we believe that an application level program can do that computation on top of this underlying framework to do the kind of processing that you would want to do. However, in terms of efficiency, that is something we haven't explored yet. That is something that is part of our future work, yes.
Hi, Charlie Johnson, HP Labs X of Tandem. Everybody should vote for Joel Bartlett's paper. The 2x node overhead is kind of a straw man. There's two ways to do this: replicated or a fault-tolerant shared disk checkpointing. Replication, if you're actually doing the log writes and the writes to the data store separately, that's like 15% overhead in the backup we have seen over time. If you're just doing the log writes, it's just a couple percent or 3%. For a checkpointing scheme where you share the disk and can take it over, the backup is only receiving checkpoints and throwing them away as progress is made, which is like 1%. And then if the primary node fails, the takeover is process by process, not by node, such that the processes are spread out on primary nodes, and you gracefully degrade the cluster as nodes go down in such a way that every node in the cluster is a primary and has backup service on it. So it's not 2x.
I completely agree with you. So yes, definitely the replication was a very Strawman solution, and there has been a lot of work beyond the 2x replication that optimizes that. But what we are trying to propose using this paper is that a completely different way of looking at stream processing systems that doesn't involve complicated backup, etc., with very low-level timing. Instead, we just use existing batch processing systems, very efficient batch processing systems, to get a lot of interesting fault-tolerant properties out of the box without using very complicated mechanisms.
So when you change your slides, it's
Sorry.
not 2x, it's 1.1 or something like that.
Moving on now. Thank you. Thank you.